Just give me 1 minute, yeah. I think I've done mute everybody, but I still can get some background noise, but I think it's okay. Okay, so now let's continue. Let's continue. Okay, on the third learning objective, you must be able to explain that the action potential must obey all or none law. So meaning that the action potential is not necessarily when you spark a fire, there will be a fire. Alright, so there must be a threshold or limit by which this action potential must reach, so that either there is an action potential or there is no longer action potential will occur. And then describe the ionic basis of the resting membrane potentials, all right? And then the different phases of the action potentials. Okay, I have a trouble over here. When you guys start coming in late, since I am outside of your organization, so I need to like admit you one by one. So please make sure that you come in the class early so that you won't disturb my class, okay? And then the last one is to explain the process of the nerve impulse conduction. So how the nerve sending the informations, when the nerve has been excited, how the information has been sent. And these informations either has been sent as an electrical potentials, or specifically they call it as the impulse conduction. So this electrical current, we call it as an impulse. So either when the question coming out, either you answer it as the electrical current, or either you answer it as the impulse generations. So it's just the same meaning. But specifically, we know it as the impulse potentials or the impulse conductions. Okay, in the excitable tissue, we have two types of excitable tissue. So we have the nerve tissue, of course, and also we have a muscles tissue. Okay, let's imagine when you are excited. Okay, when you got excited, either if you got an offer to come into the UCSI, then you start feeling happy. And then you start jumping or whatever, say yes or whatever, so your muscles start moving. So the feeling itself is actually coming from the brain. So the brain is actually the central nervous system, consists of the nerve tissue. So the stimulus is actually coming from your nerve. So there is a nerve tissue. And then when you are so happy and so excited, your muscles start moving. So this excitable tissue send an information to your muscles tissue, and then your muscles can be excited. So instead of just as the showing the feelings or what, this excitable tissue is actually a response mechanism or the homeostasis mechanism. Okay, instead of just make sure that we are in a safe mode. Okay, so what is excitability? So excitability is the ability to respond to the stimulus. So any kind of the stimulus, you could be able to have the mechanical stimulus, either by the slapping your hand, slapping of your face, give a pinch, or whatever it is that we call as the mechanical stimulus or pressure stimulus. Alright, you might also have a chemical stimulus. If let's say you have a chemical spill on top of your hand, you start moving your hand away. So we call it as the chemical stimulus. As same when you injecting a drugs or whatever it is, that is again chemical stimulus. Or you might also have the thermal stimulus or heat stimulus. So beware in mind that in our body, we not necessarily only having the mechanical receptor. We also have a chemical receptor. And we also have the what we call a thermal or heat receptor. So that's why all of this has been categorized as a stimulus for our response. So it is a property of the living cells and the organism. So every cells and every organism can be excited, and it is a result of any changes in the either electrical, means the electrical currents, the changes in the ion, okay, in the positive and the negative charge, so we call as the electrical, or either the chemical compositions inside our body, or due to the mechanical environments of the cell itself. So maybe the chemical environment is heat, so when it is heat, it can generate the movement of the ion and what so forth. Alright, so now let's move on to the resting membrane potentials. So resting membrane potential is the electrical potential difference across the cell membrane under resting condition. So right now, like I'm talking right now, I'm having an action potentials in our body and my mouth especially, okay, muscles, the auxiliary muscles on my mouth, alright? So if let's say you are in a resting state, okay, our body in a resting state are actually in a state of negative current, alright? Please remember in mind that inside our cells, inside our nerve, during resting is negative in charge, and the outside of the membrane is the positive in charge. So there is a potential. Potential is the electrical current. So the difference, alright? So there is the charge difference in our nerve, in our muscles during resting condition. So we know it as the resting membrane potential. Sometimes you might call it just the membrane potential, or it call it also transmembrane potentials, mean inside and outside. So transmembrane potentials. So its development, who made the electrical currents or the differential potentials in our nerve, is actually depending on the movement of the ion. So our body, our membrane bilayer, they have the what do you call the channels, ion channels, and these ion channels start causing the influx and efflux of a certain ion, make the electrical potentials between inside and inside of our cells. Alright, and the current, the ion itself, mostly is the sodium and the potassium. Alright, so therefore, in the membrane itself, we have the membrane and potassium pump. Okay. We're still waiting in the lobby. Alright, so let's move on to this, the imbalance in the. So in ionic imbalance between inside and the outside of the membrane is depending on the sodium and potassium pump. Okay. So we know that in our membrane potential, in our membrane itself, there has a channels, and inside the channels, inside that the embedded between in the what we call the transmembrane channels, they have a sodium and potassium, as I mentioned earlier, and we have potassium lead channels. So as the potassium lead channels appear and available there, it allows the potassium ion from the insides of the membrane to flow outside of the membrane leakily, okay, at all time. So when this potassium ion get out of the cell's membrane at all time, it's leaving the inner cells to be negative. That's why our resting membrane potentials with the activated potassium channels, lead potassium channels, causing our cells to be in the polarizing state at all times. Alright, so not balanced by the sodium influx because there are more potassium channels than the sodium channels. Okay, another reason. And then that's why the equilibrium, there is a slight instead of the cation. Cation is the positive ion from the outside, and the anion, which is the negative ion, in the inside. That create the resting membrane potentials. Alright, so let's take a look at this image. This is the inside of cells. This is a transmembrane potentials. Why do we call it as a potential? Because there is a charge difference between the external environment and also the internal environment. So we have a sodium and potassium pump, which is a sodium and potassium pump. And we know that the potassium is always leaked out of the cells. So when the potassium is leaked out and the sodium is always coming in, all right, it causes the cells, the inner layer, the inner environments of the cells to be much more negative during resting membrane potentials. All right. So the cell membrane is polarized at rest. So please bear in mind, polarized means negative charge. So whenever you heard about polar, so polar is actually a negative charge. So at resting membrane potential, you might see negative inside and the positive inside. So during depolarization is the D negative. D negative. So D negative meanings become positive. Alright, usually our cells at the resting membrane potentials, it will be negative 70 to negative 60 around. Okay, not all of the cells in our body are, not all of the excitable membrane in our body, not all of the excitable tissue in our body are negative 70 millivolt during resting membrane potentials. There are variety of the threshold, right? The variety of the electrical current difference. So usually it is negative 70 millivolts. Alright. So when the cells start to be depolarized or activated, so the charge in the positive ion will be inside and the negative charge will be flow outside. So the inner membrane will become more positive or negative depolarizations. So it will become more positive or less negative. Please bear in mind, less negative, more positive, or become depolarized. So please understand the terminology. Okay, so it will become depolarized or less negative, and the outside will become less positive. Okay, so during hyperpolarizations, when the cell, the excitable tissue start to be in a negative state back. Okay, we know that the transmembrane potentials, they have a potassium ion, and this potassium are leak potassium ion and always delay. It is not active or actively closed membrane channel. So it's always delay in the closing. So when it's delay in the closing, a lot more of potassium will be leaked out, causing the inner cells supposedly to be negative, but right now during hyperpolarizations, it will be a lot more negative, super negative. So from negative 70 millivolt, it will be negative 80 millivolt. So please bear in mind, even though the cell can be depolarized, it can be hyperpolarized, the cell later on will be equilibrate back to its normal resting membrane potential. So if let's say that excitable tissue, its resting membrane potential is negative 70, later it will equilibrate back to be negative 70. Let's say that cells must have negative 90 millivolt for the resting membrane potentials, and later it will be coming back to the negative 90 millivolt for the resting membrane potentials. So when we talk about the action potentials, when there is a stimulus, this excitable tissue will start acting an action, taking an action. So we call it as the action potentials. Just now we're talking about resting membrane potentials, and now we move to the stimulus. We give a stimulus and the cell will be start to excite. So at this phase, we call it as the action potentials. So how this action potential occur? When there is a rapid changes in the membrane potential. Alright, so usually the membrane potentials, the positive outside and the negative inside. When there is a stimulus, there will be changes in the electrical current. The inner sides of the cells will be less negative or depolarized, and the outer layer will be negative. So the changes in the electrical current between the inside and the outsides of the excitable tissue is known as the action potentials. So the spread of these action potentials begin with a sudden change from the normal resting negative membrane potentials to a positive potentials. So when we talk about the positive or negative potentials, we are actually talking about the inner cell, what happened inside the excitable tissue. We're not talking about the outside only, but we are talking about the inside, the changes in the insides of the tissue. All right? And then when it ends, it will come back to its resting potential, which is the negative potentials. All right, so in the action potential, we have 3 stages. So resting state at the beginning, and then the cell, when it's been stimulated, it will start to depolarize, become less negative. And then when it going to coming back to its original stage, it will be repolarized first because the presence of the delay potassium ion channels. the delay of the closing of the potassium ion channels causing the large efflux of the potassium ion, make it much more negative. We call it as the repolarization state. Okay. Alright, so depolarization and repolarization. Okay, I will show you about the hyperpolarization later. Okay, now let's take a look at the channels involved. Okay, in the channel involved, as I mentioned earlier, we have a sodium channels and also we have a potassium channels. So in the sodium channels, usually it is when inactivated, okay, the uppermost, at the outermost layer is the activation gate and the down inside layer is inactivation gate. During activation, the activation gate at the outermost will be open. So when it's open, it allows the influx of the sodium. So please bear in mind, at resting membrane potentials, our cell is negative 90 millivolts. Okay, let's say this is a negative 90 millivolt of excitable tissue. So during resting state, it is negative 90. When it is activated, when the activation gate is open, so the sodium start coming in, we call it as the influx of the sodium ion. Alright, and then the inner cells will be less negative. So it would be up to the positive 35 millivolt. And then when it is inactivated, so the inactivated gate will be closed and later the potassium gate will be open. So this potassium gate will cause slowly leakage of the potassium ion a lot more so that the repolarizations can occur, and sometimes when there is a delay in the closure of this gate, so it causes the repolarization. So what about the propagations of the action potential? So action potentials at least any point on the excitable membrane. So meaning that if you have a long neuron, so it can occur in the middles, it can occur in the dendrite, it can occur in the cell's body, it can occur along the at the receptor itself. So it will be anywhere. Alright, so it can occur anywhere. So this results in the propagations of the potentials along the membrane. And bear in mind, along the axon, if let's say we have a stem of the axon, if the action potential occur in between, so the directions of the action potential will go both. Alright, so then excitable tissue know that the information need to be sent over here or need to be sent over here. It depends on the cell body availables. Alright, so because we know that the neurotransmitter is only available at the axon. Alright, so it's only available at the end of the nerve. So only at the end of the nerve will be activated, and only synapse and electrical impulse will be sent at the regions that have the synapse. So meaning that the electrical current can occur in both directions, at the left or right, but at the end, only the regions that have the bulb, the synaptic bulb, and only the regions that have the synapse, that will send the electrical impulse to the next regions or next neurons or whatever, either the muscles or whatever it is. Okay. So the action potential tend to traverse in all directions instead of the stimulus. Okay, so this is how the action potential is propagated. Okay, look at this image at the during resting state. Okay, the above one, the A1. Okay, the electrical potential is negative 70 millivolt, meaning that the inner tissue is negative in charge. So when the cell is start to be excited, or when we put a stimulus on top of the cell itself, okay, the cell will start to be changed in the electrical current, the movement of the ion in and out, causing the changes in the membrane potentials, and that is the action potentials of the cell. Okay, and then the electrical current start coming in over and occur in both directions. Okay, so this is how the action potential occur. Okay, so when this is a normal potentials, so there is an electrical current changes again. So the electrical current from the inside to be from the outside to be in the inside, all right, and then the inside try to be more positive or less negative, and then the electrical current will be changed throughout directions, and at this stage or at this side, it will coming back to its resting membrane potentials. Okay. Now let's take a look at the all or none principles. Sometimes sometimes they might say, or they might write out it as the all or none law, or whatever it is. So it means that an action potential is either occur or does not occur at all. So either it is, if the condition is not right, or it does not travel. So meaning that there is a threshold or a limit by which the action potential can occur. If let's say the action potential just below the limit, so the action potential will not occur. If the action potential is above the limit, so this limit we call it the threshold levels. So if it is above the threshold level, then only the action potential will occur. Okay, so I give you, we take a rest for 2 minutes. Okay, I would like to give you, I'll stop sharing for a while. Okay, I will continue on the spinal. My computer's slow in functioning right now, but I do not know why. Okay. I'll give you 2 minutes to fill in the Google form as your attendance. So I will paste the Google form in the chat box, yeah? Slow in functioning. Sorry, my computer is loading. Okay, please check your meeting chat. Okay, I put down the link for the Google form of this class attendance. So please make sure you fill in the attendance. I'll give you 2 minutes. We will start back at 12:31. Okay. Okay, please check your meeting chat. I paste over there the meeting link. Please, the Google form link. Please fill in the Google form as part of today attendance. Okay, so for tomorrow we got 2 classes. So for tomorrow, please make sure you be punctual, yeah. Please be fair to those who coming in early. Okay. I think we have 6 person miss in this class. You only have 30. You only have 29 of you and 30 including me. Okay, so please fill in the Google form as part of your attendance, and I will continue on the spinal motor neuron. Okay. Oh, my computer is performing slow. Okay, it's okay. Alright, so I hope you can see my slide right now. It's on the spinal motor neuron. Okay, let's continue. Alright, for the spinal motor neuron, okay, we are going to talk about, we have a receptor or the dendritic zone, which usually at the terminal region, we have a receptors. So this receptor usually will attract any kind of stimulus coming in. So for example, as I said earlier, you have a mechanical stimulus, you might have a chemical stimulus, you might also have a thermal stimulus. So any kind of stimulus, all right, so it must be in a receptors, all right. And then the initial segment within the spinal cord or motor neuron, we have the nodes of Ranvier. All right, for example, that spinal motor neuron over here, this spinal motor neuron, they have the Schwann cell. So, but not all of the neurons have a swan cell. So usually the neuron that have a swan cell is actually a fast active fiber. Sometimes we call it as a neuron, sometimes we call it as the nerve fiber, alright? So it's just a similar terms referring to the neurons, okay? So those neurons that have a swan cell, okay, this is a swan cell, is actually a fast motor neuron. So fast motor neurons is for fast response. So usually in a motor neuron lah, alright? So, but you have to bear in mind that these swan cells are actually acting like an insulator. So it is a fat cells that wrapping the axon, okay, protecting the axon. But this is an insulator. So when it is an insulator, it cannot pass the electrical current. So the electrical currents in the spinal motor neurons or any neuron that have a swan cells does not pass the swan cell, but it will jump to the next nodes of Rambia. So in between the swan cell, we call it as the nodes of Rambia. So the electrical current will pass from one node of Rambia to the next node of Rambia. That's why we call it as the fast motor neuron. So please bear in mind, if let's say, what is the examples of motor neurons that is a fast motor neuron? It is a C fiber. We have a lot of motor neurons. We have a D motor neuron, D fiber motor neuron, we have the alpha delta motor neuron, we have a delta, we have a beta, and we have a C fiber motor neuron. Okay, now the axonal process, we will transmit the propagated impulse. So this is the axonals, and we have a cell body, and also at the end we have the synaptic bulb. So that synaptic bulb is actually contained in neurotransmitter, by which this neurotransmitter will start communicating with the next tissue. It's either the muscle tissue or either any kind of tissue it is, all right? Or either next nerve tissue, or it could be next excitable tissue. So, excitation, it could be stimulations by the cathode. Cathode means the positive charged electron. Okay, it's not necessarily the cathode, but this is in a lab, how they're going to measure the, how they're going to give the electrical currents, or how they're going to excite how they're going to excite the nerve cells, the nerve tissue. They give a stimulation by using a cathode. So please bear in mind that during resting time, our inner cell of the nerve tissue itself is negative in charge. When they give a positive charge to the nerve cells, they will start changing in the membrane potentials. So the action potential will occur. Alright, so decrease or reduce in the membrane potential to a certain magnitude, meaning that it will become more positive, from negative become less negative, and then it is voltage dependent, increase the permeability of the sodium ion. So when we give a positive charge, or when we give a stimulus to the excitable tissue, we start to give a stimulus to the tissue, then the sodium ion will start to open. So when the sodium ion start to open, we have a short break. Okay, when we have the excitable tissue, when we have a stimulus, the sodium ion channel will start to be activated. So there is an efflux of the sodium, and then later there will be an efflux or take out of the potassium. Then it will generate the membrane potentials, and after that, once it starts, this electrical current will separate or go to the side until they reach the synapse. So it only needs one point. So if let's say that one point exceed the threshold, then the rest or the neighbor of the cell will start to be excited. Okay, this is a threshold I showed you or I told you earlier. Instead of just a threshold, we have a sub-threshold. Sub-threshold is under threshold, or we might have the supra-threshold. So supra-threshold is the above the threshold. So if there is a sub-threshold, the cell will not be excited. Okay. And in a sub-threshold category, we have a spatial summations, and also we have a temporal summations. So spatial means half of it. Okay, 1, 2, right? Spatials. Temporal means in a tempo. So sometimes when the electrical currents or the stimulus come in tempo, we can accumulate and give one shot, and then the cell will start firing. Okay, just like you give it so many times of the electrical currents or the impulse. So this is the sub-threshold, all right? The line itself is the threshold, and this is the action potentials. Okay, here is for you to compare. We have a difference between the action potentials and graded potentials. So action potential is the one that occurs. Gradient potential is below or sub-threshold. So the action potential is propagative. It can propagate to the neighboring axon, but the gradient potential, it is non-propagative. So for action potential, it have a long distance signals, so it can travel to the long distance, and the gradient potential, it only distance signals. Okay, both depolarizing and repolarizing, and this one it will only depolarizing or only repolarizing will occur. Right? This one will obey all or none law, and this one does not obey all or none law. Summation is not possible. Summation is possible. Summations when occur when there is a gradient potential. So action potential sub-threshold occur one. We have another one sub-threshold. We have another one sub-threshold. So these can accumulate and become, we call it as the summation potential. So that's why in the gradient potential, summation is possible. Alright, this one has refractory period and this one does not have refractory period. Okay, so electronic potential is cat electronic potentials and electronic potentials. These are either the positive potentials or the negative. Okay, so cat is actually cathode, which showing a positive electron. So N is anode, which is the negative electron, okay, of the local response. So it's actually a passive changes in the membrane depolarizations is occur by either adding a positive electrical current or adding a negative electrical current to the nerve itself. Okay, nerve to the nerve tissue itself. Okay, let's say we just only give a 7 millivolt deflection. So usually we have a negative 70. When we give another 7 millivolt, it will become negative 63. But that is sub-threshold. Okay, but this actually can help the excitable tissue to start firing up. Alright, so when we give the cells the cathode or the up to the 7 or negative, 7 to 15 millivolt depolarization, so voltage gated sodium channel will start to open. Okay, while we give only 7 millivolt, we just only to trigger or give stimulus to the nerve tissue. But once the nerve tissue has been excited, it can either activate the sodium channel. So when the sodium channel has been activated, so therefore the action potential will start occurring, and that's why I said this is a local response. When the local response, we just give a small stimulations to the nerve tissue itself, so it can either activate the sodium channel so that the sodium channel can give a summation potentials to the tissue so that the tissue can reach the threshold. Alright, the influx of the sodium can reach the threshold. There you go, the action potential will occur. Okay. Alright, so let's take a look at the positive feedback cycles. What is the positive feedback cycles? We call it as the Hodgkin cycles. Okay, when you give a depolarizing stimulus at the normal situation, you will trigger the you will activate sodium channels. So when the sodium channel activate, after the depolarization, the sodium channel will become inactivate. But before that, if there is not enough current, so this sodium channel will start open a lot more and a lot more. It can cause an increase in the sodium ion and therefore bump the depolarizations or the action potentials reach the threshold, and the action potentials or the stimulus can start occur. Alright, and later it will inactivate once it has passed the electrical difference, the electrical flow to the adjacent axon. Okay, so in a normal action potential, you might have 3 stages, as I mentioned earlier. You might have the resting membrane potentials, alright. You might have the depolarization, you might have the peak itself, and you might have repolarization. And down below here is the hyperpolarization. Okay, so during this time, we call it, all of along this, we call it as the refractory period. So refractory period is the stage by which there will be no action potential can occur. Just like you give one pinch to yourself, all right, you will start feeling that pinch, feeling the sensations of that pinch. But if you give one pinch and 2 pinch, 3 pinch, you will not feel the second, and you can feel the second and third, but the information that has been sent is the first action potential that's sent to you. Okay, so meaning that during that time, there will be no action potential can be sent, there will be no action potential can occur, in between of the first action potentials. Alright, it can occur before or after hand. Alright, so during this time, the action potential, this period we call as the refractory period. Okay, so why the depolarization occur? So let's have depolarization occur due to the opening of the sodium channels. So the influx of the the influx of the 3 sodium ion, and then the repolarizations occur due to the delay closure or the closure of the sodium ion together with the opening of the potassium ion channels and cause the leakage of the potassium ion. Why the hyperpolarizations occur? The hyperpolarizations occur due to the delay in the closure of the potassium ion. So this delay causing the efflux a lot more of the potassium, leaving the cell is much more negative comparing to the resting membrane potentials. But however it is, it will coming back to its resting membrane potentials due to the leakage potassium ion. We still have a leakage potassium ion. So this leakage potassium ion will maintain the resting membrane potentials. Okay, so this is just the same. So the opening of the voltage potassium ion, it increase the potassium ion a lot more. It cause the increased outflow of the potassium out of the cells, right? And then cause repolarizations to repolarizations, and this repolarization will start to fall back to the resting membrane potential. Okay. Alright. So this is a subthreshold potential again, and this is the action potentials, and this is the resting membrane potential. So this is all under the membrane potentials. So stimulus strength, when small, greater, and the biggest one, and then later it can sum up forming a summation potentials, then the action potential will occur. Okay, now is the effect of environmental ionic concentrations on the resting membrane potentials and action potential. So when the extracellular fluid contains a lot of potassium, so the resting membrane potential will be reduced. So when we have a reduce in the extracellular fluids of the sodium concentrations, so it will decrease the size of the action potentials. Alright, and we give only little effect on the resting membrane potentials. If we have a reduce in the calcium ion in the extracellular fluid, so it will increase the excitability of the nerve, or it will increase excitability of the muscles. When you have a lot more of calcium ion, it will decrease the excitability of the nerve tissue. Okay, so changes in the excitability during electrical response, alright, and ionic electrical potentials, it will decrease its excitability. When there is increase in the ionic, a positive ion, alright, when you give a positive ion, meaning that the cell is depolarized. So when it depolarized, it will increase excitability. Okay, so period from firing level till repolarization is 1/3, so it's totally inexcitable. Okay, period from repolarizations, okay, coming back, 1/3 complete to the start after depolarizations. Okay, relative refractory period, it may respond to stimulus even stronger because it is a lot more negative and then coming back to the normal situation. Alright, after depolarization, it will increase, and after hyperpolarization, it will decrease in the excitability. Why after hyperpolarization decrease? Because it is below the resting membrane potential. So when it is below the resting membrane potentials, to make it positive back, because it is too negative. So to make it become less negative, it needs a lot more effort, or it still needs a lot more efflux of the potassium ion to go out. So the excitability will be reduced. Okay, this is the locals and also local potentials in comparisons with the action potentials. The local potential also is non-propagated. Okay, but however it can be summed. So meaning that there will be a additional stimulus that you can give a small stimulus to it, and later it can sum up and forming the action potentials. It has no refractory period. Okay, let's take a look at the impulse conductions in the myelinated and non-myelinated. Just now I did mention that in the motor spinal neuron, in the spinal motor neuron, we have myelinated axon. Alright, so that nerve fiber is actually the fast transmit fiber. So fast transmission fiber, we know it is also C fiber. Okay, usually in the motor neuron. Okay, they have a myelin, And the action potentials occur jumping from one node of Ranvier, this is a node of Ranvier, and it will occur and it will cause the changes in the sodium ion in the next nodes of Ranvier. So please bear in mind that we don't have a sodium or potassium pump on the myelin sheets, okay, on the sarcolemma, we don't have. So the pump itself is only appear on top of the nerve membrane or the axonal membrane. Okay, over here, the sodium and potassium pump is over here and only over here. So the movement of ion in and out of its pump only occur at the nodes of Ranvier and it does not occur in the myelin sheath. Okay, that's why the electrical current is jumping from one node of Ranvier to another node of Ranvier. So in comparing to those that doesn't have to the nerve tissue that doesn't have the myelin sheath, so the electrical currents occur in each whenever it passes the sodium potassium pump, though the electrical current will occur right over there. That's why those nerves that have the myelin sheath or myelinated nerve, myelinated axon, the action potential transmission is faster as compared to unmyelinated one. Okay. Alright. So that's the end of my presentations. Okay. It only takes 45 minutes to finish. But instead of that, I still have one assignment for you to complete. Okay, you can do it yourself. You don't have to submit it to me. Your assignment is to differentiate. It could be your question, yeah, your exam question, soalan bocor. Okay, so the questions would be make a difference between or identify the difference between the absolute refractory period and, okay, look at this, relative refractory period. Okay, I want you to compare what is absolute refractory period and what is relative refractory period. Okay, so what is refractory period, what is absolute refractory period, and what is relative refractory period. So I want you to go and find out by yourself, and please bear in mind that will be your exam question. It might be your exam questions. I don't want to put any question for you. Okay, that will be the end of my sessions today. Any of you want to ask a questions? Please voice out.
No, doctor.
Okay.
Doctor,
So,
that day you gave the phone number is wrong.
my phone number.
Yeah, you gave in the chat that day. We tried to message and there was someone else saying that it's a wrong number. Yeah.
Okay, I leave it one more time. Okay. Okay, so please jot down 017. Okay, I leave in the chat box. I think it's right already. Okay, I leave in the chat box. How come it turned out wrong? Alex got my number. Alex got text me. You should have asked Alex. Okay, 10.
I don't know if the other got this problem.
Yeah. Why Alex can reach me? Okay, my number is 017-4700-395. Okay. Alright. So my email norazlina.abubakar. Okay, that is my email and phone number. So please make sure that you have fill in the Google form because I will close the Google form at 1 o'clock. Okay. So for the remaining 10 minutes of our class, I want you to find out. I don't want you to waste your time. So still you have another 10 minutes to go. So please find out what is the refractory period. So what is the difference between the absolute refractory periods and the relative refractory periods. Okay. So all along the action potentials, what is actually going on? So what's this is a tip, maybe it come out in your exam, I'm not sure. Okay, what is occurring during the action potentials, meaning that during each stage of the action potentials. So during the resting membrane potentials, what makes the excitable tissue maintains the resting membrane potentials? Okay, the key information is important. And what are the things that make the action potentials or depolarizations occur? So what actually occur on the channels, the ion channels, and during the repolarizations, what is actually happening, which channel is open and which channel is closed, during the hyperpolarizations, what is actually happen, why the hyperpolarizations occur, and when there is a hyperpolarizations, they will be coming back or going back to its resting member potential. So how from the hyperpolarizations going back to the normal resting potentials, what make the resting member potential coming back to its normal situations or normal resting member potentials. Okay, so let's take a look at the so I just want to check how many of you attending my class. Oh, my computer start to be a bit slow today. Okay, we still have 30 of you, the 29 of you over here. But don't worry, I already shared the PowerPoint slide with Miss Mala. I think she going to upload it in your CN. And that's the end of our class. Thank you very much. Okay, you may dismiss. Okay,
Thank you, Doctor.
Thank you, doctor.
Thank you,
Thank
doctor.
you, doctor.